Hi, my name is Pascale Garaud, and I'm here to tell you about my research on horizontal shear instabilities in stars. This presentation is part of the Kavli Summer Program in Astrophysics, and my research is funded by the National Science Foundation. This work was done in collaboration with Laura Cope and Colin Caulfield in Dant, Cambridge, and this project was actually started at the Woods Hole Geophysical Fluid Dynamics Summer Program a few years back. An important concept in stellar astrophysics is that of rotational mixing. Rotational mixing is a fairly loose concept that describes compositional mixing or angular momentum transport that is associated with rotation. And most stellar evolution models have some prescription or another for rotational mixing. A very commonly used prescription in models today is that proposed by Jean-Paul Zahn in 1992 in his famous paper called Circulation and Turbulence in Rotating Stars. And in a little bit, I will tell you more about this paper. But if we naively think about the idea of rotational mixing, this is perhaps the mental picture we might have. Consider a star that is rotating and that is undergoing spin down from the surface by, say, magnetic braking. The surface spins down, this causes radial shear, and the radial shear might become unstable to shear instabilities and thereby drive turbulence. That causes the mixing, and voila. This is a nice and simple idea because everything is independent of latitude in this process, or at least at the 0th order level. And so you could create a model that just depends on the radius, which is very nice for stellar evolution. However, nothing is, of course, that simple. The main reason for that is that the stratification in the radiative zones of stars is usually extremely strong, and it's much too strong to allow for shear instabilities. So the last two steps of that reasoning just do not work. And to see why that's the case, we must introduce the concept of a Richardson number. The Richardson number is the ratio of the buoyancy frequency squared here to the shearing rate squared here. And in 1920, Richardson argued that this ratio has to be smaller than something of order unity for shear instabilities to be sustained. But in stars, the Richardson number is enormous, typically of order of 100,000s or tens of millions. And so shear instabilities are typically not triggered. Now, note that Richardson's argument is a non-diffusive argument. So it assumes that the turbulence would be adiabatic. Now, in 1974, in another seminal paper, Jean-Paul Zahn argued that shear instabilities can develop thanks to thermal diffusion. And in that case, the criterion for shear instability, or now so-called secular shear instabilities, must be revised. And the new criterion is that the product of the Richardson number and the Prandtl number, where the Prandtl number is the ratio of viscosity to thermal diffusivity, that product should be smaller than about 0.01 for diffusive shear instabilities to proceed. And that has now been confirmed by a number of people, including our group. Unfortunately, in stars, this product is still much greater than about 0.01. And so diffusive shear instabilities are also not usually triggered. But clearly, angular momentum is being redistributed in stars, otherwise most of them would have very rapidly rotating cores, and that's just not observed. Now, of course, magnetic fields could probably help. But historically, in stellar astrophysics, people usually shy away from using magnetic fields, and the preference has always been for non-magnetic stellar evolution models. This is changing, thankfully, but for the story I'm going to tell today, we're going to continue to ignore magnetic fields. Which brings me to Zahn's model in 92. Now, he noted that stars can also have horizontal shear, so the rotation profile omega is a function of both radius and latitude, or here, colatitude. Now, the origin of the horizontal shear can be due to several processes. It can either be due to shear in nearby convective zones, to advection by meridional flows, to thermal wind balance, and in fact, all of these are somewhat related to one another. And the presence of horizontal shear in stars is well known thanks to measurements of the solar interior. So this is an image of the rotation profile inside the sun that was obtained through helioseismology. And you can see in the tachocline region here, which is located just below the base of the convection zone, in that region, we have horizontal shear, where the equatorial regions here are rotating more rapidly than the polar regions. Now, of course, the tachocline also has radial shear, but for the story now, I'm going to focus on the horizontal component of the shear. Now, by contrast with radial shear, horizontal shear instabilities are not affected by stratification and can develop much more easily. So in 1992, Jean-Paul Zahn proposed that horizontal shear could drive very strongly anisotropic turbulence, which are often now referred to as pancake vortices. The pancakes decouple vertically and generate vertical shear on very small scales. And on these small scales, the turbulence becomes more isotropic and can then cause vertical mixing. He then went on to propose prescriptions for the horizontal mixing coefficient, d-turb HOR, and the vertical turbulent mixing coefficient, d-turb vert. The horizontal mixing coefficient is simply given by a product of a typical horizontal velocity and a typical horizontal scale. And these could be functions of, say, the local rotation rate, shearing rate, radius, and latitude. The vertical turbulent mixing coefficient, on the other hand, he directly constructs from arguments of energy transfer from the large scale to the small scales and dissipation by thermal diffusion. And in this process, he comes up with a coefficient that's given by this formula, where this SH is the horizontal shear, N is the buoyancy frequency, and this is the geometric mean of the turbulent coefficient above and the thermal diffusion. With these two coefficients, he then goes on to propose a full model that takes into account both angular momentum transport and energy transport in the stellar interior. Thermal wind balance, as described by Matt Browning in his lectures, relate the angular velocity profile to the temperature profile and to the meridional flows. Meanwhile, the angular velocity profile drives turbulence that is accounted for in these coefficients, and these coefficients themselves react back on the angular velocity profile by angular momentum conservation. And meanwhile, the meridional flows here advect and transport both angular momentum and temperature. And it is all these physics that are implemented in stellar evolution code when they implement Zahn's model, although it's perhaps not as transparent as I've shown here. But everything hangs on these turbulent coefficients that he proposed were given by these formula. So we decided to try and check whether this particular formula is valid. And this is the work that we started with Laura Cope and Colin Caulfield. To do this, we use Cartesian box simulations, which are stratified in the vertical direction with a temperature profile, and where a body force generates a horizontal shear flow. So it is sinusoidal and invariant in the vertical direction. The equations describing this model are shown here. The first one is a non-dimensional version of the Navier-Stokes equation, showing on the left-hand side the acceleration, and on the right-hand side all the forces, including the pressure gradient, the buoyancy force, the viscous force, and the body force applied to the system to drive the shear. This is the incompressibility condition for a Boussinesq fluid. And finally, this is a way of writing the thermal energy equation. And note in particular this term here, which accounts for the vertical advection of the background temperature. These equations were written in a unit system where the unit length scale is the shear length scale, and the unit velocity is obtained by assuming a balance between the forcing and the nonlinear terms in the momentum equation. That way, the mean flow that is driven is always of order 1 in these units. There are several non-dimensional parameters that come up when doing so. One is the Reynolds number, introduced by Matt Browning, which is proportional to the viscous diffusion timescale. Another one is the Pascale number, which is the equivalent, but is proportional to the thermal diffusion timescale. And finally, we have a buoyancy parameter here, which is simply proportional to the stratification. It looks a little bit like a Richardson number, but remember that here we have a horizontal shear, so the concept of a Richardson number doesn't quite work. And in what follows, we're going to vary all of these parameters, but we're going to fix the Prandtl number to be something that is small, to be specific to stellar interior conditions. The nonlinear development of the shear instability that we set up looks like this, depending on the model parameters. So these are all very high Reynolds number simulations to try and avoid the effect of viscosity. And they're also relatively high Pascale number, so that thermal diffusion is not too important, at least a priori. On the left here, we have a simulation that is not too strongly stratified, and on the right, a simulation that is much more strongly stratified. We see in both cases that the azimuthal flow, which is ux, has the form of these jets that are driven by the body force, but they're not vertically invariant, and this is because they begin to meander, and the meanders cause these alternating layers that are somewhat decoupled in the vertical. The shear driven by these now decoupled layers drives turbulence on the small scales. And the turbulence is smaller scale if the stratification is larger. And you can see this by comparing the vertical velocity snapshots in this weak stratification case to the stronger stratification case. So on the surface, remember Zahn's idea that horizontal shear leads to these pancake vortices that decouple vertically and then generate turbulence on the small scales. And qualitatively speaking, we see that this really works. And this is what we are observing here. So now let's look at this more quantitatively. And to do so, we extracted a number of diagnostics from the simulations. Here on the top left, we see the vertical scale of the eddies as a function of the stratification parameter. Top right, it's the vertical velocity as a function of the stratification parameter. And the bottom left, the RMS temperature fluctuation as a function of stratification. For very weak stratification, everything tends to a constant and simply the results of the unstratified limit. When the stratifications become significant, so in this middle part of the plot, you can see that the vertical length scale appears to scale like this buoyancy parameter to the power of -1/3. Similarly, for the vertical velocity, and the RMS temperature scales like the same quantity to the power of -2/3. For very strong stratification, on the other hand, these scalings no longer work. And these are the simulations that are marked in these open symbols. And I'll talk about them in a minute. But so can we understand first why these scalings appear in this intermediate stratification regime? And the answer is yes. These come from dominant balance arguments from the governing equations. In the momentum equation, the balance simply ignores the effect of viscosity. And you then have a balance between the forcing, the advection, and the pressure gradient. And because the forcing is of order 1 in these units, everything else must be of order 1 as well. From the vertical momentum equation, we just keep hydrostatics. And since the RMS pressure is of order 1, we have 1 over a typical vertical scale must be of order B times the typical temperature. So this is the balance here. From the temperature equation, we're going to ignore the thermal diffusion because the Peclet number is large. And so this here gives me something on the lines of temperature fluctuation over LZ times URMS, but URMS of order 1. And that must be of order of WRMS, the vertical velocity. And that gives us an estimate for TRMS. And finally, from incompressibility, dvu equals 0, but that can be divided into a horizontal component and a vertical component. The horizontal component here is of order 1, which tells us that W divided by LZ, the vertical length scale, must be of order 1 as well. And you can combine all of these equations in blue to get these very simple scalings, namely that the non-dimensional vertical length scale of the eddy should go as B, or the stratification parameter, to the power of -1/3, and similarly for the RMS velocity in the vertical direction, W. And this corresponds exactly to what we found in these plots over here. Now we can use these results to compute a vertical mixing coefficient induced by this horizontal shear instability. This is this coefficient dterb vert, which written here is dimensional. So to make it non-dimensional, I divide it by UL. And this ought to be equal to the product of the vertical length scale and the typical velocity in the vertical direction. And this we see scales as B, the stratification parameter, to the -2/3. And written in the original variables, it's the buoyancy frequency times the horizontal scale of the eddy divided by the horizontal velocity of the eddy to the power of -4/3. That turns out to be quite different from Zahn's model. And the obvious way of seeing this is that there's no dependent on the thermal diffusivity by contrast with Zahn's model. But of course, these scaling laws are only valid in some intermediate regime, remember? And they become invalid when the thermal diffusion here, which we neglected in these scalings, become important. And the simulations for which this term becomes important are the ones marked in these open symbols down here. Now, another way of saying that thermal diffusion becomes important is to say that the Peclet number based on the small vertical scale and the vertical velocity becomes of order unity. And you can then use the scaling laws that we had for W, RMS, and LZ in the previous two slides and find out when this is true. And it happens when the parameter B, the stratification parameter B, is of order of the Peclet number to the 3/2. So we can then create a regime diagram. On the y-axis here, I have the Peclet number, which you remember is a measure of the thermal diffusion timescale. So the larger the Peclet number, the less thermally diffusive, or the stronger the shear. On the x-axis, I have the stratification. As the stratification increases, B increases, or equivalently, the shear is weaker. This threshold between the diffusive and the non-diffusive regime is given by this red line here. So everything above the red line is non-diffusive. Everything below the red line is diffusive. Now, if you plug in numbers for the solar tachocline, for example, you will find that it lies exactly here in the non-diffusive regime. So this is where the stratified turbulence is non-diffusive. And therefore, the coefficients that I proposed here must apply. So in the solar tachocline, Zand's model does not apply. But on the other hand, if the shear in the tachocline were weaker, then we would be moving down and to the right in this diagram. So for stars which are much more weakly differential rotating, they might be in the diffusive regime down here. So let's analyze it a little bit better. When thermal diffusion dominates, there's a new balance in the thermal energy equation, which is between the advection of the background entropy, or the background temperature gradient, and the diffusion of the fluctuations. And this is a balance discussed by François Linéaire in 1999. You can then solve for temperature in this equation and plug it back into the momentum equation and end up with a reduced system of equation that is just given by these two. And the main parameter here, you can see, is no longer B or the Peclet number independently, but the product of the two. So in the paper by Laura Cope and Colin Caulfield and myself, we look specifically at low Peclet number simulations in which this balance is true. On the surface, they look very similar to what we saw before. We have layer-wise turbulence, which is shown here on the left, which creates this vertical shear on the smaller scale that then drives vertical shear instabilities. Since the governing parameter is now the product of the buoyancy parameter and the Peclet number, we can plot everything in terms of that. So in the top left here, we have the vertical scale of the eddies as a function of this parameter. Here we have the vertical velocity as a function of this parameter, and here we have the RMS temperature fluctuations as a function of this parameter. And again, we can see that when plotted that way, everything collapses onto a single line. And in this intermediate regime, which is the one we're interested in, the vertical length scale goes as this buoyancy Peclet to the -1/3. The vertical velocity goes as buoyancy Peclet to the -1/6. And the temperature fluctuation go as the Peclet number times buoyancy Peclet to the -5/6. So these are quite different scalings from what we obtained before in the non-diffusive regime. And again, we can use arguments of dominant balance to try and explain where they come from. So from the temperature equation this time, we neglect the advection of the temperature fluctuations and end up with just this balance. And this then predicts that the vertical velocity should be 1 over the Peclet number times the RMS temperature fluctuation over some typical vertical length scale squared, which gives us this equation. From the horizontal momentum equation, again, we find that the RMS velocity in the x direction, and it should be both of order 1, just as before. But now, crucially, in the momentum equation in the vertical direction, we no longer just have hydrostatics. As it turns out, the nonlinear term in the momentum equation also begin to matter. And so in this particular case, we have a slightly new balance, which is given here. URMS, WRMS over LZ is BTRMS. And of course, again, URMS is of order 1. And we can take all of these equations and combine them, and then we obtain the scalings that we actually found in the simulation. So the vertical length scale goes as this combined parameter to the -1/3. The vertical velocity goes as this parameter to the -6. And so the vertical turbulent diffusivity, which you can construct by multiplying this typical vertical length scale with typical vertical velocity, goes as BPE to the minus 1/2. And that turns out to be exactly Zan's model's prediction for the turbulent vertical mixing coefficient associated with horizontal shear. So now we can go back and re-identify the regimes in this diagram that I discussed earlier. Everything above this red line is a non-diffusive regime, which is the new regime where the turbulent mixing coefficient is different from Zan's model. But below this red line, we are exactly in Zan's regime, and the vertical mixing coefficient is exactly the one he predicted. And again, the solar tachocline is up here, but stars with weaker differential rotation might be in Zan's regime. So to conclude, from a qualitative perspective, the picture is very much consistent with what he had in mind. The horizontal shear instability drives very strongly anisotropic turbulence with pancake eddies that are much broader in the horizontal direction than in the vertical direction. They decouple in the vertical, drive vertical shear, and it's the vertical shear-induced turbulence that causes vertical mixing. But the results are not completely qualitatively consistent. It depends on the regime in which we are. In the diffusive regime, Zan's model applies, but there's also a new non-diffusive regime found where the mixing coefficient is quite different. So all of this tells us that horizontal shear instabilities could be a significant source of mixing in stars, but must be modeled correctly. And I encourage you to look at these papers for more information. Now, as part of the projects proposed in this program, we are going to include other effects, such as rotation, a mean vertical shear, and look at nonlinear instabilities as well. So I encourage you to ask me more questions if you're interested.